Hello all. In today's session, we'll be discussing about different line coding schemes. We'll uh, see the implementation of different line coding schemes with Python. So quickly, we'll be going through what are the different line coding schemes. Then we'll see how to set up Python environment with Anaconda for implementation of these line coding schemes. And finally, we'll go through the Python code for line coding schemes. So first we'll see what are the different line coding schemes. So basically line coding schemes are used to convert the digital data into digital signal. Okay, so what do you mean by digital data and what do you mean by digital signal? We'll shortly see it. So these are the different line coding schemes. So specifically line coding schemes can be categorized into these five categories. In today's session we'll be looking at the Python implementation as well as description of the unipolar NRZ scheme, then polar NRZ, RZ, Biphase Manchester and differential Manchester, as well as we'll be discussing the AMI scheme from the bipolar line coding schemes. Right, so this NRZ is nothing but not return to zero, RZ is return to zero, while in case of polar scheme, NRZ schemes can be categorized as NRZ-I, that is NRZ invert, as well as NRZ-L, that is NRZ level. Okay, that is non-return to zero level, non-return to zero invert. While there are different biphase polar schemes, which are called as Manchester and differential Manchester. Generally, this Manchester scheme is used in the Ethernet communication. Right. So let's see how the digital data is represented using digital signal in the unipolar NRZ non-return to zero scheme. Okay. So in case of NRZ scheme, all the signal levels are only on one side of the time axis. Signals are represented above time axis or below time axis. So here you can see that this 10110 is nothing but your digital data, right? So this digital data we want to represent in the digital signal form. Okay, so by using this unipolar non-return to zero scheme, you are converting digital data into digital signal. So this is nothing but the digital signal, right? So these line coding schemes are specifically used at the physical layer of the TCP/IP model. Okay, so as you know that in case of TCP/IP model there are 5 layers: physical layer, data link layer, network layer, transport layer, and the application layer. So whenever you are transmitting data through physical medium, right, so your digital data should be converted into digital signal format, right? So therefore these line coding schemes are utilized for that. So there are certain advantages and disadvantages of all these line coding scheme. So the best line coding scheme should be selected for representation of digital data or conversion of digital data into digital signal format, right? So as you can observe, in case of unipolar NRZ scheme, the signal, this particular signal is represented only on one side of the time axis. So this is your time axis, right? So signal can be either above time axis or it can be below time axis. So currently in this diagram you can observe that signal is represented above time axis, right? So for representing digital data 1 or data bit 1, the high voltage level is utilized, right? So consider here just for example 5 volt. Okay, so 1 is represented by using value 5 volt, okay, or the voltage level 5 volt, right? So it is not compulsory that always you should represent the data bit using the high voltage levels. If you are representing one with high voltage level, or even you can represent one with the zero voltage level. Okay, so graph will be exactly opposite if you are representing one with the zero voltage level, right? So it is simple that one here represented with the 5 volt value, right? Then for 0 is represented with the 0, right? 0 volt. Again 1 is represented with the 1 volt value, okay, as well as again next one is represented with this 5 volt value, that is higher volt value, and then again 0 is represented with the 0 voltage level, right? So even you can represent it uh, alternatively, right? That is, one can be represented with the 0 voltage level, while 0 can be represented with 5 voltage level, right? So this is simple unipolar NRZ scheme. So in case of this unipolar NRZ scheme, if you are representing uh, data, okay, similar data, if I am representing, that is 1 0 1 1 1 1 0, by using or below the time axis, just for example. So here if I am using negative voltage, just for example minus 5 volt for 0, and for 1 I am using 0 uh, as an as a voltage, right? So in that case this particular graph, okay, below time axis can be uh, represented in case of unipolar non-return to 0 scheme is simply I'm using 0 for 1, and then minus 5 volt for, just for example, 0, right? Similarly again 0 volt will be used for 1 1, and again minus 5 volt for 0. So this is nothing but what? Unipole NRZ not return to 0. And basically this scheme is called as non-return to 0 as it is not crossing the time axis, okay. The signal, digital signal, is not crossing the time axis. This digital signal will be below the time axis, or it can be above time axis. So this is unipolar NRZ scheme. Next one is the polar NRZ scheme. So polar NRZ schemes are categorized into two categories, that is NRZ-L, that is nothing which is called as NRZ level, while another category is the NRZ-I, which is nothing but the non-return to 0 invert. So in this case the voltages are on both sides of the time axis, right, as it is polar scheme, right? In case of unipolar, why it is called as unipolar? Because the signals are on only one side of the time axis, either above or below, so therefore it is called as what? Unipolar scheme. But these in case of NRZ-L and NRZ-R, these both schemes are the polar scheme, because voltage are on both sides of the time axis, okay. That means your signal, digital signal, will be crossing the time axis, okay. So in case of NRZ-L, the level of voltage determines the bit value, okay. uh, Whatever voltage level is there, it will be utilized to represent the data bits. While in case of NRZ-I, the inversion of bit, or the inversion of signal, or the lack of inversion, determines the value of the bit, okay. Let's see what does it means. So here the NRZ-L scheme has been indicated in the first graph, while in the second graph the NRZ-I, that is NRZ invert scheme, has been indicated. So again, this is your digital data 0 1 0 0 111 0, okay. This is nothing but the digital data, and the digital data is converted into these two digital signals by using two different digital line coding scheme, that is NRZ-L and NRZ-I. So in NRZ-L, so if I'm considering again it as 5 volt, right, this is your 0 volt, and this will be, just for example, minus 5 volt. So in case of NRZ-L, the voltage levels, okay, voltage levels, how many voltage levels are there? Just for example, 3 voltage levels are there. So 5 volt is the first, 0 volt and minus 5 volt, just for example, right? So the higher voltage level is used to represent the data bit 0, while negative voltage level minus 5 volt is used to represent the data bit 1 in case of NRZ-L scheme, okay. So 0 is represented by the 5 volt or the positive voltage level, while 1 is represented by using negative voltage level, right? So again, for next two bit, zeros are 0 0, next two bits are 0 0, therefore it will be represented by using positive voltage level. next 3 bits are 1 1, so these are represented by using negative voltage level. Similarly, the last bit is 0, again it is represented by using positive voltage level, right? So in case of NRZ invert scheme, inversion of signal will be carried out at 0 or it can be carried out at 1, right? So in this case, the inversion of signal is carried out when next bit is 1, correct? So for 0 bit there is no inversion. Okay, inversion means simply signal is getting changed. Okay, it will be crossing axis. So for 0 bit there is no inversion, but for 1 bit there will be inversion. So you can observe that. So as first bit is 0, so as you are representing 0 with the positive voltage level, so 0 is there. So basically you can even start this signal from here, right? So if you are starting from negative voltage level, the signal will be something different. So whenever one will be occurring, signal will be inverted, right? So as you can see there, so initially signal is starting from this particular positive voltage level, but next bit is 1, so therefore inversion has been carried out here. Okay, so signal is getting inverted, right? Again it will follow the path as the next 2 bits are 0 0, so no inversion will be carried out. That means it will remain in the same path. Okay, that is, it will be represented by using same voltage values. Again the next bit, that is nothing but here the 5th bit is 1, so again signal will be inverted. Again here next bit occurring is 1, so therefore signal is inverted, right? Again next bit which is occurring is 1, so again signal will be inverted. Then again here you can observe that next bit is 0, so signal will not be inverted. So there uh, this is how the digital signal is represented by using a non-return to 0 inversion scheme, okay, or invert scheme. So basically both these schemes are polar schemes because signals are represented using voltage level on both sides of time axis. Next polar scheme is the return to 0, right? So signal will always return to 0 irrespective of what data bit values are there and what voltage levels are used to represent those data bit values, right? So it basically in case of return to 0 scheme, okay, so these three values of voltages are utilized, that is positive, negative and 0, because signal is always returning to 0, right? So the main disadvantage of this return to 0 encoding, it requires two signal changes to encode a bit, and therefore it occupies or it requires more bandwidth. As you can observe in the previous diagrams, single bit has been represented by using signal component, right? But in case of RZ scheme, you require two signal changes. So let's see how those two signal changes will be required. So here you can see the polar return to 0 scheme has been utilized. Your digital data is 0 1 0 0 1. This is your digital data. So now you can see that 0 is represented by using negative voltage, right? But during this time duration, right, during this first bit duration, the signal is returning to 0, correct? So for representing 0, there are two signal changes, right? One is 0 is represented by using negative voltage, and again signal is returning to 0, so that means 0 level is also utilized. So 0 is represented by using negative voltage as well as 0 voltage, right? So two signal changes are there, so therefore it requires more bandwidth compared to NRZ-I, NRZ-L as well as unipolar NRZ. So again one is represented by using this positive voltage, again signal is returning to 0, right? Next bit is 0, so 0 is represented by using negative voltage, again signal is returning to 0, right? Next bit is again 0, so signal is represented by using negative voltage and again it is returning to 0. And finally last bit is 1, so it is represented by using positive voltage and it is returning to 0. Okay, so this is nothing but polar return to 0 scheme. Okay, the next schemes are biphase polar schemes, Manchester and differential Manchester. So basically this Manchester is the combination of NRZ-L and RZ scheme, while the differential Manchester is the combination of NRZ-I and RZ scheme, right? So always again you require two signal changes for representing single bit in case of this Manchester and differential Manchester scheme, correct? So let's see how data will be represented. So here you can see the data is 0 1 0 0 0 1. Okay, so this is a digital data represented by using these two digital signals. Okay, so these two digital signals are generated by using Manchester and differential Manchester line coding scheme. So again you can see that there are two transition of signal in the single bit duration, right, or single time slot. So here 0 is represented by using positive level. Okay, so Manchester is the combination of NRZ-L and return to 0. So 0 is represented by using positive voltage, while 1 is represented by using negative voltage. So but it is the combination of NRZ-L and an RZ that is returned to 0. So signal will be always returning to 0, right? So signal getting returned to 0, 0 is represented by positive voltage, signal is returned to 0. 1 is represented by using negative voltage, signal is getting returned to 0 again, right? Next bit is 0, 0 is represented by positive voltage, signal again return to 0. Then next bit is again 0, 0 is represented by using positive voltage, right? So again signal will return to 0. Next bit is 1, 1 is represented by using negative voltage here, right? Again signal is getting returned to 0. Again next bit is 1, so 1 is again represented by using your negative voltage, right? And again signal is getting returned to 0. So this is how NRZ-L and RZ schemes are combined in case of Manchester line coding scheme. Next one is the differential Manchester. Differential Manchester is the combination of NRZ-I and RZ scheme, that is non-return to 0 invert and return to 0 scheme. So again signal can be started, just for example it is started from here, and inversion will occur either on bit 1 or on bit 0, right? So here the inversion is occurring when bit is 0, while when bit is 1 the inversion will not be occurring, right? So signal is started from here, but signal will be, as first bit is 0, so it is represented here, or signal is getting started here, but signal will always return to 0. As you can see that next bit is 1, for 1 bit there is no inversion, so therefore signal will continue here, but again signal is returning to 0, right? While next bit is 0, so therefore you have to perform the inversion, so therefore signal is getting inverted here. If next bit here was 1, so signal will continue in this direction, right? Signal will continue here if next bit is 1, but as next bit is 0, so therefore signal is getting inverted here, right? Again signal will return to 0. Again the next bit is 0 here, right? As it is 0, so again it will be inverted, right? Signal is inverted, again signal will return to 0. Now next bit is 1, right? So there will not be any inversion, so signal will continue here. But as it is a combination of NRZ-I and NRZ-I and RZ, so as next bit was 1, signal was not inverted, but signal will return to 0 here, right? So signal was returned to 0. Again next bit 1, so no inversion will be there, signal will continue, but again signal will return to 0. So this is how your Manchester and differential Manchester schemes will be encoding your signal, or representing your data, digital data, using digital signal. The last scheme that we'll be discussing here is nothing but alternate mark invert, right? So basically this mark terminology has been taken from the telegraph, right? So mark is nothing but simply 1. So whenever 1 will be occurring as digital data, you will be inverting the signal. Okay, so that is the simple concept of this AMI scheme, that is alternate mark inward scheme. So same thing has been indicated here in this graph. Your digital data is 0 1 00 10, right? So as you can see that for 0 voltage value has been utilized, right? Whenever 1 is occurring, so 1 is represented by here using positive voltage level, right? Again 0 are represented by using 0 voltage level, but one for next one the signal is inverted. Okay, so this mark are nothing but the one. Okay, mark are nothing but this one. So whenever the one are occurring in the signal will get inverted, right? So initially one was represented using positive voltage, next one will be represented by using negative voltage. If there is again next one, so that next one will be represented by using positive voltage. Likewise, whenever one will be occurring, signal will be inverted. So this is nothing but the alternate mark invert scheme. So all these line coding schemes implementation will be looking in the Python. We'll be writing Python code for all these line coding schemes. But as it has been indicated in the previous slide, there are some additional line coding schemes, but we'll be limiting our discussion up to the alternate mark invert scheme. Okay, so now let's see next how to set up the Python environment for carrying out these implementation of line coding scheme with Anaconda. So specifically, what is Anaconda? So it provides various features. So you can simply execute the individual code snippet in the IPython interactive environment provided by the Anaconda. So these executions can be carried out in the Anaconda prompt. Directly you can execute the code snippet. Okay, that is the block of codes or the lines of code, some limited lines of code in the IPython environment, right? Or you can directly execute the complete application, which is simply called as scripts. So scripts are generally stored with .py extension in the Python, right? So these .py extensions will be utilized to indicate the Python scripts. Okay, so our Python scripts can be saved with the extension .py simply. So these complete applications can be simply executed using the Anaconda prompt. Okay, so in case of Anaconda prompt, you have to simply execute the command, that is Python, and the name of the script, just for example line coding.py. Okay, or there is another web-based environment provided in the Anaconda, which is called as Jupyter Notebooks. So it is a convenient and interactive web browser-based environment in which you can write and execute code, as well as you can intermix your code with the text. So text can be utilized to describe your code, or you can even insert images in it, or you can also insert videos. Okay, so these are not the part of the Python code, but these things will be simply used for the description of your written Python code. So these three things are provided in the Anaconda, okay, which comes with the Python and R distribution, right? So this Anaconda can be downloaded from www.anaconda.com if it is not already installed in your system. So you can simply download it from anaconda.com. So it has some different libraries, okay, provided with this Anaconda. Default libraries of Python, right? So as you visit this anaconda.com, on the page you can directly get the option for downloading this particular Anaconda, right? After downloading Anaconda, you can simply install it, right? So simply executing its executable or installer file, right? It may be installed in macOS platform, it can be installed in Windows, or even it can be installed in the Linux environment, right? Or Linux operating system, Unix based or Linux based operating system. So on Windows, you can open the Anaconda prompt from the start menu, right? Simply you have to type Anaconda, right? After installation, you can type Anaconda there, right? So you will see the option there for Anaconda prompt. So here the Anaconda which I have installed had come with the Python 3.8 distribution. So you can simply right click on this Anaconda prompt and you can run it as administrator. Okay, so that is the process on Windows operating system. In case of Mac OS, you can open terminal, okay, from the application folder. uh, Inside that application folder you will have utility folder, so under that you will find terminal, and on terminal you can directly execute the Python commands, right? And on Linux you can simply open the system terminal or simply shell. Okay, after installing Anaconda, you should update Anaconda by executing these commands. Okay, first command is the conda update conda. So that conda update conda will be simply executed in the Anaconda prompt. So here, once you open this Anaconda prompt, you will get this command prompt right here, that is Anaconda prompt. So you can switch out of these directories Windows System 32 simply by typing cd/cls for clearing screen, and here you have to execute these commands for updating the Anaconda. So first command you will execute conda update conda. As I have already executed this command, so my environment is already updated, so I will not be executing it right again. So next command that you have to execute is the conda update all. So initially you have updated the Anaconda, next you are updating the all the libraries available with the Anaconda, right? So along with that, you will be installing the Prospector static code analysis tool. So this is used for analyzing the code that you have written, right? As well as you will be installing the Jupyter Matplotlib extension. So basically this Jupyter notebook is the interactive environment, web-based environment used to write your Python code, while Matplotlib is used for the visualization purpose. If you want to graph the data, you want to represent the data using various graphs, so you can use the Matplotlib. As we have seen in these line coding schemes, you will be representing digital data using digital signals, right? So those digital signals will be plotted, right? So we'll be using Matplotlib for plotting those signals. Okay, so again you have to install these things. So for that purpose, again on Anaconda prompt you will be executing the first command, that is nothing but pip install prospectors. Okay, so here on GitHub you can see the description of Jupyter Matplotlib extension, right? So basically this can be simply executed, these commands should be executed, that is conda install c conda, that is -c conda forge ipy-mpl. Okay, so this will be installing your Matplotlib extension for the Python, and then you can also install Node.js libraries, right? Then you will be executing this Jupyter Lab extension for Jupyter Lab through Jupyter widgets, right? And finally you will be executing this again, that is Jupyter Lab extension install Jupyter Matplotlib, right? So one command that you need to remember, that is conda install c conda forge, right? And in front of that you have to specify the name of module or library that you want to install, right? So this Anaconda provide various packages. So Anaconda comes with approximately 300 popular packages of Python and data science. So Anaconda is utilized for executing your machine learning codes, even data analytics codes, right? So those codes can be written with the support of already existing popular Python and data science packages, or you can additionally install required libraries which you need to write your codes. Okay, so again, it can be installed by using, as I have said, that conda install c conda forge, right? So this can be installed simply by using typing the command conda install c conda forge, right? Conda dash forge, right? And in front of that you have to specify the name of library or module that you want to install. So just for example, if I want to install numpy, okay, so when I'm executing my code, so I'm getting error, no module, right? No module present, or no module error. So in that case, you need to install that module simply by executing this command on the Anaconda prompt. So command is conda install -c conda forge and the name of module. So just for example, if I want to install numpy, right? So this command will be executed on the Anaconda prompt. Or even you can, if you want to install matplotlib, so you can have conda installs -c conda forge the matplotlib, okay, the name of library, correct? So the last part of today's session is the Python code for these line coding scheme that we discuss, or the line coding scheme which we have discussed in this session, right? That is nothing but your unipolar NRZ, then polar NRZ-I, NRZ-L, RZ, right? Different, and the biphase scheme in the polar scheme, that is nothing but the differential Manchester and Manchester, and finally the bipolar scheme, that is AMI, alternate mark invert. Okay, so let's see how to execute that code. I will describe that code later on. Okay, so this is the code that I have written for uh, for demonstrating all this line coding scheme. So as you can see that the first statement that I have inserted in this code is nothing but import matplotlib. So I am using matplotlib for plotting the graphs, okay, signal graphs for the entered digital data. Okay, so I have stored this particular script, okay, in this particular folder, okay, that is G, on G drive. Under that different folders are there. Inside that line coding folder is there. Okay, so the name of my Python script, as we have seen, you can directly execute the code snippet, right, in the IPython environment, or you can directly execute Python script, or you can use Jupyter notebook, right? So we are executing the Python script using Anaconda prompt. So I already started this Anaconda prompt, right? So I need to go to G drive, right? So I have typed here G colon there, correct? And then I will simply copy this particular path, okay, and I will type here cd, and I will paste that path there, and I will enter. So currently I am in that particular directory, line coding. So I will simply execute that Python script, line coding.py, by typing Python, and in front of that the name of the Python script. So it is line coding.py, right? So I will simply press enter. So here what has been asked there, so just I will, okay, so I'll just increase the font so that, okay, so here you can see that what has been asked there, enter the size of data to be encoded, right? So just for example, if I'm entering the size of data is 8 bits, now it will be asking for enter those bits in the sequence, right? So 1, then 0, just for example 0, then 1 1, right? How many bits? 5 bits I have entered, right? Then 0, 1, right? So now, okay, one more bit has been remained. So I have entered 8 bits as 1001 1010. So I'll just enter here, right? So the graph will be generated comprising all the coding schemes that we have discussed. So here you can see that the first one, okay, just a minute. Oh, it is not responding. Fine. So first, the graph plotted is for unipolar. As we have seen in case of unipolar scheme, the signal will present either above time axis or below time axis. So in this case, it is present on above the time axis. Our data, as you can see here, just I will take it downwards. Just reduce some font here. Just a minute. Okay. So as you can see here, our data is 100111010. So here you can see that 1 is there, right, in the first time slot. Then 00, right, has been represented, correct, 00, and again there is 11, right. So this upper wave has been represented 11, then again 0, then 1, and last bit is 0, right, as you can see in the data that we have entered there. So in case of unipolar NRZ, okay, so this label also has been given on y-axis, right, unipolar dash NRZ, correct. So as you can see that this unipolar NRZ label has been given, right. So okay, so unipolar NRZ, so your signal is present above the time axis. In case of polar NRZ-L, as you can observe the graph as well as the values assigned on y-axis, those are varying from -1 to 1. Okay, so negative voltage and positive voltages are utilized, but in case of unipolar NRZ, only positive voltage has been utilized there, right. So in case of polar NRZ-L, your negative voltage and positive voltage is there, right. So in this case, the 1 is represented by using positive voltage, while 0 is represented by using negative voltage, because it is L, okay, that is level has been utilized, voltage level has been utilized to represent the data bits. Okay, similarly you can observe the remaining graphs. If you observe the NRZ-I, right, so where the signal has been inverted, so the signal is inverted for bit value 1. Okay, so whenever there is bit value 1, then signal will be inverted, otherwise it will not be inverted, right. uh, just a minute. Okay, so signal, if you observe this signal, initially 1 is there, right, so next bit is 0, so it is continued, right. Then whenever next bit is occurring, so according to that the signal will be inverted. The description that we have seen in line coding scheme, so you can observe accordingly how those signals has been inverted. And then next scheme is basically your polar RZ. Okay, so as you can observe that every time duration has two signal changes, right. So again in case of RZ, for one it has been started from the basically the 0 is represented by using negative voltage values, while 1 is represented by using positive voltage value, right. But again in case of RZ scheme, your signal will return to time axis. Then there are differential Manchester, bipolar Manchester, B underscore man has been given as Y label, okay, Y axis label there, and differential Manchester scheme. So Manchester scheme is the combination of RZ and NRZ-L, while differential Manchester is the combination of your RZ and NRZ-I. And then you can observe the graph for alternate mark invert, right. So whenever one occurring, so your signal will get inverted. Zeros are represented by using simply 0 voltage level, but for 1 signal will be inverted. So first bit was 1, so you can see the positive voltage is utilized for representation of first one. Next two bits are 0 0, as you can observe here, right. So next two bits are 0 0. Then the fourth bit is 1, so signal is inverted there. Next one is represented by negative voltage. Again next bit is 1, so this will be represented by using positive voltage. Again next bit is 0, so 0 value will be utilized. Next bit is 1, so initial one was represented by using positive voltage, so therefore this one will be represented by using negative voltage. So this is how this graph will be generated. Okay, this graph comprising overall the 7 different subgraphs here. So now let's see the description of the code, how it has been written, right? So we are importing, or we are using this matplotlib.pyplot library as PLT. Okay, so PLT name will be utilized to access the functions or modules defined inside the matplotlib.pyplot library, right? So you will be using PLT as a name. So execution will be started from this block of code. Okay, so initially what it has been asking for, so it is asking for the enter the size of encoded data. So this message will be displayed, right, using the print function, right? And whatever value, as you can see there, here the message has been displayed, that is nothing, enter the size of encoded data, okay, or data to be encoded. So as I have entered here 8, so that 8 from the input will be accepted, it will be converted to integer, and it will be assigned to variable size. Okay, so your size will be holding value 8. Okay, so the size will be your value 8, right? Then I have taken one list. Currently this list is empty, so the purpose of taking this list is simply for appending the values or the bits that will be inserted afterwards. Okay, so for getting uh, bits from the user as an input, I have again displayed the another message by using print statement. So where I have displayed enter the binary bit sequence of length. So here this variable name has been passed, so whatever value size will be holding, that value will be displayed here, right? So as you can observe there, enter the binary bit sequence of length. As I have entered the size as 8, so 8 has been automatically displayed here. Okay, for that purpose I have accessed that variable using its name size. Okay, and I have separated those two substring. This is the first string, right? So this string is ended here, this is the variable name, and again I am appended the next string there. Okay, that is bits, and followed by the carriage return /n, right? So again the user, after this particular message, entering the 8 bits. Okay, so it will be only taking 8 bits, and then you have to wait for it so that it should generate the required graph. Okay, so as you can see that one by one I have entered those bits, right? So depending on the what is the size that you have entered here, so I have entered 8, so this for loop will be iterating for 8 times, right? And one by one whatever input I am entering there, right? So first input that I have entered there is 1. Okay, so again that will be converted into integer, and that will be appended to list. Initially the list was empty, right? List was empty. Now the list will comprise first data, that is nothing but 1. Okay, next similarly one by one those bits will be appended in the list. Okay, so once I have the list comprising all those data bits or the data, I'm passing that list in the function plot. Now this plot function is defined here, so this is nothing but the user defined plot function. Okay, so this is how you will be defining functions. So I'm simply writing def plot and the variable that I'm passing to it colon. Okay, so this is the definition of the plot function. So in this plot function, as you can observe that plt was the name that I have given to the module matplotlib.pyplot. So I'll be accessing the functions from this module using plt as a reference, right? So here I have just specified plt.subplot. So subplot function has been called. So in subplot I'll be there will be 7 subgraphs, right, inside a single figure. As you can see there are 7 subgraphs, right, in 7 rows basically, but there is single column. Okay, single column, and it is the single figure. Okay, so figure 1 comprises basically these 7 graphs. So therefore I have passed to it 7 comma 1 comma 1. Then I have given the y label to the first graph as unipolar NRZ. Okay, you can assign any label to it, but it should indicate the what coding scheme I am using. So here you can see the y label unipolar NRZ. In similar manner, for each graph I have given the y label, right? So you will find y label after the block of code. So after assigning the y label, then for plotting the graph, I am calling individual function for which has been written for each individual scheme. So as you can see in the above block of code, you will find different functions has been defined here, right? So first function defined is the unipolar, okay, then polar NRZ, L, polar NRZ-I, right? And to each function again I am passing the list, right, which I have taken from the user comprising the data bits. So here you can see that first function I am calling for plotting the unipolar NRZ graph. Okay, so I have passed list here. The color of graph is red. Okay, so you can see the color of first graph is red, right? Next draw style is steps free. Okay, if you do not specify this draw style, so you will get the continuous graph, okay, as an analog graph, right? So here for getting this graph in what you can say square wave form or digital form, you need to specify here this draw style as steps free, and marker used here is greater than sign. As you can see the markers here during transition or change of bit, so marker has been indicated there. Okay, for every signal transition as well as data bit transitions. So this is how this code has been repeated. Okay, this block of code has been repeated for each scheme. Okay, so this is nothing but 7 graph has been plotted. They only in one column I am plotting first graph, then second graph, then third graph, right, then fourth, and so on up to 7 graphs, right? Y label has been assigned, right? For plotting, plot is the predefined function, right? Basically whatever I am calling, and here also I am overriding its definition, right? So plot has been again defined uh, inside this code itself, right? So here I have overridden it, so whenever I am calling it as simply plot, right? So here it has been called as plot. So here the function which is defined by me will be called, but whenever I am calling the function as plt.plot, so in this case the plot function defined in the matplotlib library will be called, right? So similar sort of code is there simply for plotting different signals using different lines coding schemes. The functions has been defined here. Now let's look at these functions. Okay, so let's look at this function, how those function has been passed, sorry, defined. So here first function for unipolar NRZ, here list will be passed. Now this list will be assigned to input 1 as it is. Then in input 1 I am also inserting data 0 comma 0, and I will be simply returning the input. Okay, so input will be written as it is basically, right? So because in case of unipolar scheme, you are simply plotting the data. Okay, you are not changing anything, right? As you need to represent data on the above time axis, okay, or you have to represent data about the time axis, so nothing has been changed in that data. But if you observe the polar NRZ-L scheme, right, so if the data bit is 0, then it will be represented by using -1, or if data bit is non-zero, that is 1, then it will be represented by using one value. So therefore you will observe in the polar NRZ-L scheme, your graph will be on both sides of axis. Okay, so -1 and 1 is also utilized, and the axis is represented by using zero value. Okay, bit present in between that 1 and -1, that is high voltage level and low voltage level, right? Again, this INP is nothing but the list, that is Li, right? Again, I am assigning that list to temporary variable here, INP1. Okay, input 1, then I am again inserting 0, right? Correct. So for getting exact what it is inserting, so here also you can print the INP1. Okay, so below this you can insert the statement print in bracket INP1, so that you will get to know what has been inserted there, right? And I'm checking in the this input one, if value of bit is 0, then -1 will be utilized, that is negative voltage will be utilized for its representation. And if value of bit is non-zero, right, so 1 will be used. Okay, so this will be done for all I in INP1. Okay, so depending on how many bits are there, so I have taken 8 bits. For 8 bits these values will be assigned, either -1 or 1 will be assigned, right? Similarly, in case of polar NRZ-I, so I'm inverting the bit. So I have taken one additional variable here, that is nothing but lock. So initially I am assigning or keeping that lock as false. So that means it is a Boolean variable. It can have value false or true, right? True or false. So again, Li has been passed. It has been assigned to the temporary variable, and I have taken the lock as false, right? Because I have to invert the signal. Okay, so whenever for the inversion bit that I have taken, right? So again, depending on how many bits are there in this list, right, because input 2 comprising my list Li passed to this function, right? So if the value of that bit is 1, then you will be converting lock to true. Okay, and you will be continuing, right? And otherwise, if your log, that means if it is true and your input bit is 1, then what you are doing, so you will be changing that bit, right? Correct. So the previous bit will be changed to 0 and the current bit will be assigned value 1, and you will be continuing. If lock is false, right, so in that case input bit will be 0 and you will be continuing, right? And so these values, right, these values will be assigned to this input 2 depending on the current value of bit and the current position of the lock, right? So I will be the ranging, okay, depending on the how many elements are there in the input. So we have 8 elements, right, in input. So we are checking here if the input of I is 1 and it is false, right, so you are changing lock to true and you are continuing, right? So that means you are not changing any bit, right? But if this particular condition is not met, so you will be checking for the next condition. In that case, if lock is true, right, and the input bit is 1, right, so in that case what you are doing, you are changing the initial bit value as 0 and current bit value as 1 in the input, right? And then again you are continuing. If this condition is not satisfied, right, so in that case the input value assigned will be 0, correct? And similarly, if your lock is true, in that case you will be assigning the previous bit value to the current bit value. So you are simply updating the list here. Okay, so whatever data that we have entered here, 100111010, okay, so all that data bits will get inverted and then you are checking the condition. So if data bit is 0, then it will be represented by using negative voltage level, and if it is non-zero, then it will be represented by using positive voltage level. So this is nothing but invert. Then RZ, in case of RZ scheme, again this Li is passed here, temporarily assigned to input 1. Then you are modifying input 1 as, so as you need to assign two different signal components there, so you will require two different lists and you have to append it, right? So in this case what you have done, so uh, because your signal, if you observe this polar RZ, so single bit will be represented by using two signal changes, so those two signal changes should be done here. So if -1 is there, right? So sorry, if bit value is 0 is there, then it will be represented by negative voltage or it will be represented by positive voltage. So this is your first list, right? Then you have taken the second list. So again, depending on the length of the list that you have generated here, depending on the levels of voltages, right, then you are appending that list into the empty list, right, and then you are appending 0 to it, right? So for every I, after every bit in the list, the 0 will be appended. Okay, so just for example, first bit is represented by using -1, then after -1 0 will be there, right? 0 will be appended. Next bit is represented by 1, right? Positive voltage level, again 0 will be appended, right? In our case, the INP1 will be comprising value 1, -1, -1, 1, 1, -1, 1, -1, because for 0 we are using, just a minute, uh, okay, for 0 we are using -1 there, correct? So therefore, likewise, our this list, INP1 list will be comprising 1, double -1, double 1, -1, 1, -1, and then after every data bit 0 will be appended. So 1 0, -1 0, -1 0, 1 0, 1 0, -1 0, 1 0, -1 0, right? So the length of, or the total number of elements in Li will be 16 instead of 8, right? Similar sort of logic has been used in case of Manchester. Again, list has been passed, right? So because it is the combination of your RZ and the NRZ-L scheme, right, from the polar scheme, so the logic used in those two cases has been combined here, right? List has been appended, right? You can observe here, list has been appended there, but only the thing is that you have to return, you have to cross, okay? Your signal will not remain at the time axis, that is with the value 0. It will cross that axis, either it will cross up to positive voltage or either it will cross up to negative voltage. Here we are representing the voltage values by using 1 -1, but it is not compulsory you should use it by using 1 -1. Even you can take 5 -5, right? Here you can take -5, here you can take 5, right? In previous case also, where you have represented is at -1, 0 is represented by -1, 1 is represented by 1, even you can represent it by -5, and here you can represent by 5, right? So according to that, the values represented in the graph will be changed, right? So again, here you can see that some additional variables has been taken, right? So empty list has been taken, as lock has been used here. I am using init, so initially it is false. IMP1 will be comprising my list, okay? So I am modifying this uh, list here, that is Li, right? So if I input 1, that is list comprising the first or bit as 0, then -1 will be appended. If not, not init means if it is false, init is false, then Li will be appended with -1 simply, and then init will be taken as true and list will be appended with 1 again, right? So again, here you can see that input 1 is there, right? If bit is 1, this logic is for bit bit. If you are representing 0 bit value, this will be for 1. So 1 will be represented 1 simply, and it will be appended with -1. So your signal should cross from 1 to -1. So therefore, if you observe the graph for the Manchester coding, so you will find the two transitions during the time duration in that course of time. So similarly, the differential Manchester, so it is the combination of your what you can say, return to 0 and NRZ-I. So you need to invert the bit. Okay, so whenever there is change in bit, right? So for that purpose, I'm taking a pre list here. Sorry, I'm taking the list here as empty, right? Lock I am again taking to invert the bit. So initially it is false, and pre it is represented as Z initially, right? So here these, if you observe these graph for the differential Manchester, so you will come to know about the logic here, right? So this variable pre is simply used to check the condition for inversion. Okay, so if you find here, if pre is s, so simply inversion will be from -1 to 1, otherwise it will be from 1 to -1. And again, uh, inversion will be carried out either at 0 or either at 1. So therefore, if you observe the pre, if it is set as z, right, you will changing pre to s, right, and then you are changing the inversion from -1 to 1 here, correct. And then all these things are appended in the list li, and li will be written for plotting, right. So if your pre, right, is not z, then you will be changing it to z, right. So either these statements will be executed, right, or the above statements will be executed, right. So finally you will be assigning the values inside list li, right. So again, you can print the values inside the li, right. So initial li was passed from the main function here, so it was comprising 8 bits. So 8 for 8 times this for loop will be executed. It is checking the if the bit is 0 and if it is false, right. So for 0 you will append -1 in the list, right. Again you will append -1 in the list, and you will append 1 in the list, and you will change lock to true, and you will set pre is equals to s. And if it is not if bit is not 0, so in that case, if bit is 1, so you will append 1 and 1, right, so to represent that particular bit. And if you will change it or transit from 1 to -1, right. And again the lock will be changed to true, and z will be set there, right. So, and otherwise in both cases, if it is not the condition, that means lock is true, right, then in that case, this input, and if input bit is 0, right, if both conditions are not matched, then this block of code will be executed. Input for input bit 0 and input bit 1, right. So that means your pre has been set either to s or either to z. According to that, transitions will be carried out, right. So last is the AMI, correct. So in this case, again, the input has been comprising the list content. You will be inserting 00 to it. You are changing lock to false, because again whenever you are inverting bit, in this case AMI, only bit inversion will be carried out for 1, right. So here you can see that the conditions are checked only for bit 1 values, right. So it will be whenever that bit value is 1, so you will be changing it to -1, or you will be keeping it as it is, right. When lock is false, bit value initially kept as it is, you have changed it true. That means for next uh, 1 bit value, and as you see that lock is true, it will go and change or represent that one with -1. Again you are changing lock to false, right. So if again next 1 is occurring, so in that case again this condition will be true, because lock is false, right? You are simply changing lock is true. That means you are representing one with positive voltage, right? So now lock is true. Next again one is occurring. Now your lock is true here, right? And one is occurring there, right? So it will be represented by using negative voltage. So that is the simple logic here. And to get into all exact logic of it, right? So you can take a page and pen and simply whatever input that you are providing here, you just manually execute this code for the input, whatever input you will provide. It is not compulsory that you should simply provide 8 bits and 8 bit as input. You can simply start with simple 4 bits, but those 4 bits should be different, right? Some variation should be there to observe the actual changes, how these functions are processing those inputs. So you can simply take a pen and paper and try to execute this code manually. Okay, so that's all for the code. Okay, so just I am scrolling this complete code here. Okay, starting from the first, right, function, that is import. Then next is the definition for it, right? Definition for unipolar, definition for polar. Next, definition for polar NRZ invert, right? Correct. Next, polar RZ. Next, Biphase Manchester is there, right? Differential Manchester, and finally your AMI function, where we are calling all these function inside the our defined function plot. This plot function has been called. You can take any markers or colors there, not necessary all these colors or same color should be utilized, right? Only the thing is that you should call the exact function. This is the final main function there. So that's all. Thank you.